Hi, my name is Chukwemeka Ike. I'm a PhD student in the ECSE department, and I'm going to talk a little bit about the design of an optimal controller for a mobile robot. A little bit of an idea of what the presentation is going to look like. I'll start off talking about the motivation behind the actual project before I talk about key topics that are necessary for understanding what went down under the hood. I'll talk about metric temporal logic, mixed integer linear programming, the satisfiability problem and its extension into SMT before I actually talk about the actual controller design for the project. So to start off, I'll talk about motion planning for mobile robots. It's a key competency for a robot to be able to get from one point to the next while avoiding collisions and remaining efficient with respect to some metric, be it that you want to minimize the amount of time that it took to get there or minimize the amount of energy that was used in getting there. There have been numerous approaches to the problem, either sampling-based ones, which put out a bunch of random points into the mapped environment and then check for collisions, and then try to basically interpolate between the source and all the series of points to the destination. There've also been the idea of potential fields that kind of decompose the overall map into a field with attractive forces coming from the goal and repulsive forces coming from the obstacles. And so that particular approach actually falls into is prone to the problem of local minima, kind of trapping the robot, but I'm not going to talk about that right now. One major thing, though, is that temporal ordering kind of becomes a problem for these approaches. If you want to specify that a robot gets from one point to the next and then to a third location, it becomes a bit of an issue. And so that's why I'm going to then go into the next slide and talk about metric temporal logic. The metric temporal logic provides an extension to propositional logic, which we probably all know about. It adds time ordering operators, which kind of allows it to provide a more natural task specification framework for dynamical systems. If you think of the statement that the robot must never enter the obstacle region and must eventually reach a goal set, can be expressed very readily in metric temporal logic. So the uses are in sequencing, temporal placement, which is kind of what I mentioned already, and in coverage. If you want to specify that a robot must reach every point or every station in the map, you could do that readily with MTL. So now I'll talk a little bit about MTL formulas. They're usually made up of three major things: atomic propositions, your logic operators, and your temporal operators. And they're always defined on some form of interval, either true or false for that given interval. I have an example here that the syntax is defined as follows. Phi is equal to always not in the obstacle region and eventually getting to that goal region. And breaking this down a little further, we have the atomic proposition, which I'll get to a little later when I talk about the controller design. And you have your usual conjunction operator and your negation operator. And so talking about the actual MTL syntax in this formula, we have until, which isn't directly in the formula. Until, exactly as it sounds, just means that one formula holds until another holds. Then building upon this, you have the eventually formula, the eventually operator, which is defined basically as the universal truth until phi happens. So phi happens at some point on that interval, whenever, and then you eventually go on to the always operator, which just means that at no point will phi evaluate to false on that interval. And so they all are basically defined exactly as they sound, and it gives you a pretty natural way of expressing whatever specifications it is you have for that robot or for that system. To switch gears a little bit, I'll be talking about mixed integer linear programming now, or MILP, and its optimization as we already know it to be from this class, with the added constraint that one of the optimization variables has to take on a discrete or an integer value. It's used in situations that involve discrete decisions, as you can expect. Operations management, electric power production, robotics. Specifically for this project, it was using the actual collision avoidance or staying away from the obstacle region, which I will show a little further on when I talk about the controller design, but I just wanted to prime you up a little bit about it. So I just wanted to show you a really basic MILP problem where we're trying to optimize some cost function or subject to some constraints where x and y are optimization variables. And the real key thing here is the fact that you can see at this very last line that x and y are some combination of the positive reals, positive integers, and binary values. And so that last part, the binary portion, is what we actually use in formulating our MILP problem to solve the issue of staying outside of the obstacle region for the robot. And you'll see that a little further down the line. But real quick though, I just want to go into the next slide and talk a little bit more about the last topic of interest. The satisfiability problem is a decision problem that asks if there is a way for a given Boolean formula to evaluate to true. It is then concerned with finding a satisfying model if that is the case. Some of its applications are in hardware verification, task scheduling, and model checking. And one thing about SAT solvers is they're highly efficient and automatic, because there's been so much research into the field that though the SAT problem is an NP complete problem, there has just been so much tweaking of the algorithms that these solvers use that it's to the point where they're really highly efficient. And so the idea behind this project, part of the idea behind this project, was to see if I could use a SAT solver to solve that optimal control problem and generate a resulting trajectory for the robot. However, SAT solvers only work at the Boolean level, and so there is a need for some kind of extension that allows the addition of other background theories, and that's where SMT comes in. SMT allows you to then add your integers and your reals and equality and so on to your problem, and they're important because these SAT solvers are already pretty efficient, but systems are usually designed and modeled at a higher level than Boolean. And so SMT solvers aim to combine SAT solvers with specialized theory solvers to find solutions to systems of constraints. And so that's where it starts to tie into the overall idea of this class, where we aim to optimize some objective with respect to some constraints. The constraints are provided by the metric temporal logic formula and also by the dynamics of the system. And the objective function was the sum of the input energies, which I'll detail a little further in the next set of slides. And so now I'll actually detail the design of the controller. I'll start off by talking about the model that I used, discretizing that model, and then formulating the optimization problem that was used by both solvers to generate a trajectory for the robot. And so now I talk a little bit about the model that I used for this system. I used a simple kinematic model with the derivative of the pose being its xy coordinates and its angle, its heading angle with respect to the world frame, which you see right here is q dot is equal to x dot, y dot, and theta dot. And I've framed that in terms of its velocity, its actual like linear velocity and its angular velocity. And then I used a method of feedback linearization from nonlinear control. It was a method used in a paper that I was going over to kind of get that, represent the state dynamics in terms of its accelerations in the x and y directions, and then inverted that rotation matrix to eventually lead me to the inputs being those accelerations. So I assumed that I could directly control the x and y accelerations of the robot for this controller. And so with that model in mind, it was simply a matter of discretizing it so I could actually cast the problem as a MILP problem. And so I used Newton's laws of motion and a sample time of 0.1 to get the equations in front of you. And those laws, I'm referring to the equations that the final velocity is equal to the initial velocity plus the acceleration times time. And then the position is equal to the initial position plus the amount of time that has passed times the initial velocity plus a half of the square of the time times the acceleration. And so if you look at this, your ux is your acceleration, x1 is position, x2 is velocity, and it's the same for the y coordinates. And so now I want to just rehash the control objective now that you have all the information in front of you. The idea was to start at the initial position, avoid the obstacle region entirely, and enter the goal region with minimum energy. For the first problem that I will show you, we don't consider the station, while the second one tries to reach the station at some point within that interval from leaving the start to getting to the goal position. And so for the first problem, we simply want to get to the goal while avoiding the obstacle region. And so it becomes a problem of minimizing the sum of the squares of the input energy subject to that MTL formula and the dynamics of the system. And so looking at it, our objective function then turns to this: over the entire 351 time step interval, we want to minimize that sum of the squares. And we always want to stay out of the obstacle region, which is encoded as this. The atomic proposition that I mentioned earlier is this: keeping it out of the obstacle region, it's either that we need x1 to be less than 5 or greater than 6, or we need y1, the y position, to be less than 3 or greater than 9. Any one of these being true would automatically mean that the robot is outside of that obstacle region. And we want to eventually, at the end of the interval, get to that goal square that was shown in the previous slide, which is x from 8 to 9 and y from 8 to 9 as well. And so now we formulate the mixed energy linear program based on the previous slide. One thing to note, however, is that the condition to keep the robot outside of the obstacle region was made up of or statements. You had either x1 was less than 5 or greater than 6, or y1 was less than 3 or greater than 9. And there's no way to directly translate your or statements into a mixed integer linear program. And so I use the big M formulation, which is in reference for, I believe, an MLP approach to controller synthesis. And it essentially introduces this M, which is a very large number. In my case, is a very large negative number that makes sure that one of these inequalities at any given time evaluates to true, one of them or all three. Essentially just making sure at least one is true at any given time. And so based on that, we can then we have the inequality constraints and the equality constraints here with the initial conditions. And so we can then pass this overall MLP problem to the Gurobi solver to generate a feasible trajectory to the goal. And so I used the Gurobi optimizer in MATLAB to solve the MLP problem proposed in the previous slide. And it produced a trajectory that you see on the right side where the robot goes through that pretty quickly because it's a sped up video. But essentially it stays out of the obstacle region and eventually gets the goal region as specified by the mixed integer linear program. And so that's a success. And so the second problem was really similar to the first one with the added constraint that at some point in that interval, it eventually visits the station, the blue station that was shown in the workspace. And so it's the same objective function right here, but it has the added constraint over here that at some point in that interval, we need for the robot to be within that station region. And so I'll go on to show you how that was formulated as an MILP problem. And so for this problem, it's quite almost identical to the original problem formulation, with the additional fact that this Z5, this additional decision variable, which basically makes sure that at some point in the simulation horizon, these inequalities evaluate to true. And so these would essentially ensure that the robot at some point in that trajectory enters into the station before getting to the goal. And so this overall then builds the entire MLP for the problem 2, and then the inequality constraints, the equality constraints can then be passed to the Gurobi solver to generate a trajectory for the robot to the goal. And in similar fashion to problem 1, I then took that overall MLP problem as formulated on the last slide and plugged it into the Gurobi solver to speed up the calculations. And you can see the trajectory does pass through the station, and it eventually goes avoiding the obstacle to the goal region. One thing I want to mention is how close it gets to the obstacle region. A number of planners do a thing where they inflate the obstacle region and try and prevent that sort of thing from happening in the physical world, to where even if the trajectory plan is too close to the obstacle, it's an inflated obstacle. So the robot doesn't actually get too close to the physical obstacle. I want to see if there's a way I can encode something similar into the MLP problem, but that's a future work type of situation. I included this slide more as on an honorable mentions type of thing, because the original idea behind this project was to build an SMT-based planner to solve the problems that I have solved using MILP now. I used the Microsoft Z3 SMT solver, which has no problem with disjunctions, so I didn't have to take that extra step that I had to with MILP, where I used the big M reformulation of the problem to get away from those OR statements. One issue though is that I was unable to minimize quadratic cost functions, and so I ended up trying to minimize the sum of the inputs, which, if you're thinking about it, had the issue of trying the acceleration is always tending towards negative or trying to tend towards 0 even when not necessary. But overall, the problem came from a flaw in my algorithm, which was I was unable to figure out how to encode properly that goal region. And so even though you see that the robot does satisfy the constraints in keeping with its dynamics and staying out of the obstacle region, it wasn't able to head toward the goal at any point. And this was only one of the trajectories that was generated, but none of them ever seemed to want to go to the goal. And so that's more of a future work thing for me, where I want to figure out how to do that, how to encode goals so that not only does SMT solver optimizing my objective, but it's gradually tending towards something each time. And so I'll just go over the conclusions and future work for this project. One thing we saw was MTL providing a powerful tool for encoding time-ordered tasks, where we were able to get the robot to do things at certain times, either from eventually getting to that station or eventually getting to the goal. And not just MTL, but temporal logics. There's a whole list of other temporal logics, which I didn't mention, but they're being used in a plethora of applications that involve ordering tasks in time with respect to time, and they just provide a more natural way of expressing these specifications. MLP provides a repeatable framework for then optimizing objectives constrained by MTL, and not just MTL again, but also just temporal logics in general. And so that's that for the conclusions. For future work, I want to, like I mentioned already, really tweak that SMT algorithm to account properly for the goal configuration to get it to actually tend toward a goal. And then I want to also seek out possible alternatives to the Z3 solver so that I'm able to minimize quadratic costs, which is one of the issues that was with my algorithm in this project. And so that's that. Thank you.